Hi, everybody. Whew. So today we're going to start a new topic, having left nomenclature behind. And now we're going to start talking about strain and the limits of molecular stability. We talked about how resonance stabilizes molecules. So what we're going to talk about mostly this week is features of molecular structure that destabilize molecules. And that is what strain does. Strain destabilizes molecules. And there are a couple of different kinds of strain, five or six different kinds of strain, but we're going to limit our attention to to three of them. First kind of strain that we want to talk about is angle strain. And this is caused by a deviation from the ideal bond angle. So angle strain, this is caused by deviation from the ideal bond angle. This is sometimes also called ring strain because it usually occurs in rings, but it doesn't have to. So, for example, if we look at cyclopropane, we know that the carbons in cyclopropane are sp3 hybridized. Their ideal bond angle is 109.5 degrees. But when we look at this little triangle, which is our representation of cyclopropane, we see that there's no way that the carbon-carbon-carbon bond angles are 109.5 degrees because it's an equilateral triangle pretty much, and the angles, the interior angle of an equilateral triangle are 60. So we can comment that this angle here, this angle right here, this wants 109.5 degrees of bond angle, but it's 60 degrees. So that's a huge deviation from ideality. And the deviation from ideality, this is what introduces angle strain. Now, what is happening here is that the reason that something like this destabilizes the molecule is because these carbon atoms are still sp3 hybridized. And believe it or not, the orbitals, the sp3 hybrid orbitals at each of these carbons are still form 109.5 degree angle measurement, but they are not along the bond axis anymore. So if we made a big picture, just to show that, big picture of cyclopropane, we'd get something that looks like that. And here's an sp3 hybridized carbon atom, and it has an sp3 orbital that way, right? And it's making this 109.5 degree angle with all of the other sp3 hybrid orbitals. We didn't make this big enough. Let's make it big like that. And this carbon over here, he's also sp3 hybridized. The atomic orbitals at this carbon are also arrayed along that, pointing to the corners of the regular tetrahedron. And so when these two orbitals overlap, we see that this is not, this interaction here, it's not the optimal head to head interaction, right? The ideal situation would be there's one sp3 hybrid orbital and there's another sp3 hybrid orbital, and they're interacting head to head. But because of the bond angle, because of this 60-degree bond angle here in cyclopropane, now the bond angles aren't head to head. Now they're kind of, off kilter, so that the overlap, so here the overlap is weak. And so this is what causes the angle strain. And we see that if we were to look at the other rings, the 3-membered ring, the 4-membered ring, so on and so forth, we would see a fairly smooth progression of strain energy. Much of it, but not all of it, due to angle strain. Okay, so deviation from bond angle, that causes deviation from the ideal bond angle, that causes angle strain. Angle strain destabilizes the molecule. All right, so now I guess one of the things we should talk about is exactly by how much the molecule is destabilized by various strain interactions. So we can make a little plot here, and we call this E strain, and this will be the ring size for the 3-membered ring, the 4-membered ring, the 5-membered ring, the 6-membered ring, the 7-membered ring, the 8-membered ring, and so on and so forth. Okay, and this axis up here, maybe let that be about 120. That's about 110, 80, 60, 40, 20, something like this. And this is in units of kilojoule per mole. Well, it turns out that the 3-membered ring, the cyclopropane, has a strain energy of about 115 kilojoules per mole. A lot of it, but not all of it, is caused by angle strain. There are other strain interactions that we're going to talk about later. But now, as the ring opens up, the 4-membered ring, well, that's going to be an interior angle of 90 degrees. That is still not 109.5, but it sure isn't 60. So when you go from the 3-membered ring to the 4-membered ring, the bond angles approach ideality a little bit better. This strain drops down to maybe about 110 or 109 or something like that. It's not a huge drop, but it's significant. The 5-membered ring, where the interior bond angles are now 107, right? Because a pentagon, the interior angles of a pentagon are 107. Oh, that's really close. That's pretty close to the ideal bond angle of sp3 hybridized carbon. So the angle strain falls way, way down. It's somewhere maybe around 10 or something like that, 10, 15, something like that. Now, the 6-membered ring, which we'll be spending a lot of time talking about, cyclohexane, has no strain at all. All of the strain interactions have been relieved. And now, as the ring gets bigger, strain once again plays a part. And the 7-membered ring has strain of about 15, the 8-membered ring a little bit higher, or something like that. So we have this nice curve which shows that the 5-membered ring and the 6-membered ring, they're the best. But the 7-membered ring, the 8-membered ring, now they begin to have a little bit more strain interaction. Okay, so the strain of a 3-membered ring is about 115 kilojoules per mole. Well, now I guess it's interesting to talk about, well, what exactly, how much strain is that? So this figure up here for the three-membered ring, it's about 115 kilojoules per mole. Now, I guess, let me venture to say, maybe I'm wrong, but let me venture to say that that number means nothing to anybody, 115 kilojoules per mole, unless you're some kind of heat transfer engineer or something like that. Okay, so trying to put a human face on 115 kilojoules per mole, maybe you've heard of ammonium nitrate. Ammonium nitrate. Okay, this is ammonium nitrate. This is a demolition explosive. And so perhaps you remember or have heard about the act of domestic terrorism that was perpetrated by Timothy McVeigh when he bombed the federal building of Oklahoma City. Well, there, the explosive that was used there is ammonium nitrate. And when ammonium nitrate detonates, when this thing detonates, it releases about 120 kilojoules per mole. So the amount of strain in the three-membered ring is comparable to the amount of energy that is released when an industrial demolition explosive is detonated. So that's quite a bit. That's quite a bit of strain, I would say. Okay, so strain. So angle strain. That's the first kind of strain that we're going to talk about, and that is due to deviation from bond ideal bond angle. All right. So let me give you a little problem here. What about this guy versus this guy? Okay, they are isomers. They are constitutional isomers. They have the same formula, same degrees of unsaturation, all of that. So this is a fair comparison. Circle the more strain. Which of these do you think has more strain? Tell me in the chat. The guy on the left or the guy on the right? So which of these has more strain, would you think? The guy on the left or the guy on the right? Oh, it's going to be the guy on the left. Sure, because he has two strained carbons, right? He has these, this is sp2 hybridized. It wants 120 degrees. It's getting something close to 60 here. This guy has two strained carbons. This one only has one. This carbon up here at 12 o'clock, he's pretty free. He doesn't have any, doesn't really have not confined into a ring. So this guy is more strained. Why? Because he has more strain. I mean, because it's more strained carbon atoms. Now, before I leave strain and talk about ring angle strain and talk about the next kind of strain, a word about the triple bond. You know, like on a piece of paper, I can write, I can put a triple bond inside a three-membered ring, right? No problem. The paper didn't blow up, right? The paper didn't catch fire or anything like that. I was able to write it. And also on a computer screen, putting a three-membered ring in putting a triple bond in the three-membered ring, I mean, the computer doesn't blow up or give me an error message or anything like that. But the smallest ring that can accommodate a three-membered ring is an eight-membered ring, right? This guy here, he's impossible. Too much strain. This is sp hybridized. It wants 180 80 degrees. It's confined into this ring with 60 degrees. There's just way too much strain in there. So the smallest ring that can have a carbon-carbon triple bond is an 8-membered ring. Okay, so just a little note there about ring strain and the alkyne functionality. Okay, so next kind of strain is steric strain. And this occurs when big, bulky groups approach each other too closely. And the bigger and bulkier they are, the more strain is going to happen. Now, the origin of steric strain is something that I think maybe you met in Gen Chem, and that is valence shell electron pair repulsion. Remember VSEPR? Well, that's what causes steric strain. This is caused by so-called non-bonded electron, that's my little symbol for electron, caused by non-bonded electron pair repulsion. And so this is a very confusing name in my opinion, because non-bonded electron, well, that's something, but that's not what's happening here. What is meant by non-bonded electron pair, this means electrons that are not in the same bond. Electrons in the same bond, that's stabilizing. That's the quantum mechanical effect that leads to bond formation. So when electrons are in the same bond, they behave like waves. They stabilize each other as they form a chemical bond. But when electrons aren't in the same bond, now they just take on the characteristic of a negatively charged entity, and negative hates negative. So, for example, if we were to draw something like, let's say, this molecule here, it looks like those chlorines are 1,000,000 miles away from each other. How could these chlorines possibly interact? But it turns out that if you were to make a computer model of this or a physical model of this, you'd see that these chlorines are actually quite close together. Let's draw something a little bit more realistic. Maybe if we were to draw, maybe, let's see, maybe put this on edge. Put this on edge like that. And I'm going to make this bond down here big and fat. That shows that it's closer to you. And I have a Cl sticking up there and a Cl sticking up there. And remember that these lines, these represent orbitals, right? This is real, it's not really a stick that's holding these atoms together. These are really orbitals that are inhabited by electrons. And this chlorine is surrounded by a sea of electrons of its own. So that, although this is how we will conventionally represent this molecule, we have to keep in mind that this is actually a big sea of electrons, like that. Let's represent the orbital looking like that. And now this carbon-chlorine bond, that's also a big sea of electrons. Let's represent the orbital looking like that. And we see a zone of interpenetration right in here. where the electrons in this carbon-chlorine bond are interacting repulsively with the electrons in the neighboring carbon-chlorine bond, right? When I draw it like this, it looks like the chlorines are a bazillion miles away from each other, but they really aren't. And furthermore, these aren't little balls and sticks. It's an atom that is surrounded by a sea of electrons. And so I have here a repulsive zone of interaction. Okay, this is the origin of steric strain. It's that these chlorine atoms, they're big, they're bulky, they have gotten too close together, and the electrons that surround these atoms are now interpenetrating the zone of electrons inhabited around the other chlorine atom. So this is what causes steric strain. It's called non-bonded electron pair repulsion. Okay, so when big bulky groups get close together, we get steric strain. All right, so let's see, let's do maybe a little problem here. What about something simple? What about something like this? Versus something like that. Okay, circle the one that has more strain. Which one do you think it is? Tell me here on the chat. Oh, it's going to be the one on the right, sure, because this methyl group is a big ball of carbon and hydrogen. It's surrounded by a sea of electrons. There's a hydrogen here, right? Can't forget about him. And he's surrounded by a sea of electrons as well, but hydrogen is small. So maybe his sea of electrons is like that. And we see maybe something like that. There isn't that much interpenetration. And then this methyl group is surrounded by a sea of electrons as well. So something like that. There's a hydrogen here as well. So maybe that's the situation over here. But in this guy, this 1,2-dimethylbenzene, we have a big sea of electrons around this methyl group that has now interpenetrated the sea of electrons around the neighboring methyl group, and that is causing the steric strain. Okay, the next kind and the final kind of strain that we're going to be talking about is called torsional strain. Torsional strain. And torsional strain, it's called this because this is the kind of strain that is relieved by twisting. Relieved by twisting. Okay, and the origin of torsional strain, once again, just like with steric strain, is caused by non-bonded electron pair repulsion, just like steric strain is. Okay, so to understand what exactly is going on here with steric strain, let's look at a little molecule. Let's look at a little tabletop. Draw this little tabletop here. And I'm going to put a carbon atom here. And I'm going to put a Cl bonded to a Cl. I'm going to put a carbon atom there and bonded to a Cl there. Right? And there are other bonds involved. The carbon has other bonds. I'm just going to ignore them for the moment. And when these two carbon-chlorine bonds all lie on the same table, that is where, on the same plane, on my little tabletop, this is where torsional strain, this is where the strain is maximized, because we just said that this carbon-chlorine bond is actually a big sea of electrons like that, And this carbon-chlorine bond is actually a big sea of electrons like that. And there's this zone of unfavorable, repulsive interaction where negatively charged electrons that aren't in the same bond are interacting with other negatively charged electrons that aren't in the same bond. Okay, so when the carbon chlorine bonds all lie on the same tabletop, we can say that these carbon chlorine bonds, the carbon chlorine bonds, are eclipsed. Just like when the moon gets between the sun and the earth, that's an eclipse. Okay, and so this kind of bad interaction, this is relieved by twisting. So what are these bonds? What is this bond going to do? Is that this carbon-carbon bond is going to twist. So let's look at this a little bit later. There's the sea of electrons surrounding the carbon-chlorine bond, and the carbon-carbon bond twisted out of the way in order to relieve that bad interaction. Oh, you see those carbon-chlorine bonds, they're not on the same plane anymore. They have, in order to relieve this bad eclipsing interaction, the carbon-carbon bond has twisted out of the way. And so now these bonds aren't eclipsed anymore. They don't lie on the same tabletop. And the repulsive zone of interpenetration has been relieved. Okay, so that's what torsional strain is. This is also called eclipsing strain, right? Torsional strain, this is also called eclipsing strain. All right, there are other kinds of strain interactions, but we're not going to get into them. Just want to confine ourselves to these three types of strain. The classical way of showing torsional strain is the Newman projection. And this is a new way of looking at sp3 hybridized carbon. It's called the Newman projection because it was devised in the 1950s by Professor Edward Newman of the Ohio State University. And this is one way of showing torsional strain, and it's another way of looking at sp3 hybridized carbon. The Newman projection. Okay, this is a way of looking at sp3 hybridized carbon. Okay, so in the Newman projection, to formulate a Newman projection, what we do is we sight down a bond, and the carbon atom in the front of our line of sight is imagined to be residing in the center of a disk. And we can see everything that is bonded to the carbon in the front, except the carbon in the back of the bond along which we are sighting. And the carbon in the back, we can see everything bonded to it. Okay, so let's look at how to formulate a Newman projection. So if we were to imagine up to now whenever we draw sp3 hybridized carbon, we always draw two solid lines representing bonds in the plane of the paper, and a dash and a wedge. And so these wedges represent bonds that are pointing toward you, and these dashes represent bonds that are pointing away from you. Okay, so there's our dash and wedge picture of sp3 hybridized carbon. That's what we've been using up to now. All right, so now let's decorate this molecule with all kinds of crazy substituents. Maybe I'll put an NO2 group up here, maybe a hydrogen there, a Cl there, an F there, and maybe a methyl group there, and maybe a hydrogen over here. Okay, and so now what we want to do is we want to sight down a carbon-carbon bond. So I'm going to put my eye over here, right? That's supposed to be my eye, and I'm sighting down this bond. And what do I see? The carbon nearest to me in the bond down which I am sighting, that is imagined to live at the center of a disk. So I'm going to put like a little star, maybe. That's this guy here, right? And I can see what is bonded to that carbon up in the front there. I see a nitro group sticking straight up in the air, right? I'm over here and I look at this molecule and I see on my right and pointing to 4 o'clock, I see the Cl. And on my left, pointing to 8 o'clock, I see the hydrogen. Okay, so that's the carbon in the front, in this Newman projection. All right, so now in the carbon in the back, that is hidden by this imaginary disk. I can't see the carbon in the back. It's hidden by this disk, but I can see everything bonded to the carbon in the back. So what I see is a methyl group pointing straight down to 6 o'clock. And then I see on my right and pointing to 2 o'clock, I see the fluorine. Okay, so now check this out. You see how that bond was interrupted here, right? This disk, this imaginary disk, I'm not drawing this line to intercept the star here. I'm cutting the bond off so that I'm getting this three-dimensional perspective. And then I see a hydrogen on the carbon in the back pointing toward, on my left and pointing toward 10 o'clock. So that's the Newman projection of this molecule. But it's not the only one, because the Newman projection is going to change. Its appearance is going to change depending on my vantage point. So I could also imagine myself standing here, right? And I'm sighting down this bond. But now the Newman projection is going to look different because my vantage point has changed. From this vantage point, I see the carbon in the front. I'm going to put a little square on him, right? The carbon in the front now, that's the little square. I can see him and I can see everything bonded to the carbon in the front except the carbon in the back, which is hidden by this disk. So what do I see now? Now I see a methyl group pointing straight down to 6 o'clock. I'm looking at it this way. I see a fluorine on my left pointing to 10 o'clock. I see a hydrogen on my right pointing to 2 o'clock. Okay, now what about the carbon in the back? The carbon in the back is hidden by the imaginary disk. I can't see it, but I can see everything bonded to the carbon in the back. So I see that nitro group pointing straight up like that. I see the chlorine on my left and pointing toward 8 o'clock. And I see that hydrogen on my right pointing toward 4 o'clock. So there's another Newman projection of this very same molecule. It looks different, but because my vantage point has changed. Okay, so let's see. I brought some, you can investigate the Newman projection on that. If you're lucky enough to be taking the lab, you can investigate that Newman projection using that Avogadro thing. But I just have some physical models here. I don't know if this is going to, how this is going to work. So let's just see. Let's just try this out. All right. Okay, so this is what, let's see. I guess what you would be looking at now, that's the that's the dash and wedge, right? That's the dash and wedge. That would be a solid line. The orientation here. That would be the solid line. That would be a solid line. This would be the solid line as well here, right? And this would be a bond pointing toward you, away from you. So this is just the dash. That would be the dash and wedge representation. In the Newman projection, you are sighting down a bond. You're putting a carbon in front. Let's see, you're putting a carbon in front. Okay, so that kind of looks like the Newman projection, sort of, right? Okay. And again, if you have models, if you bought physical models, it's fun to play with. And if you are looking at that, if you're doing the lab and have figured out how to use that Avogadro program, you can also look at Newman projections on there as well. Okay, so let's do a problem where we're drawing Fisher projections, shall we? Okay, what about draw a Newman of, oh, let's invent some kind of crazy molecule here. How about 1,2-dibromo 1-chloro 1,2-dibromo 1-chloropropane. Right? You're supposed to be able to come up with these structures, right? From the name, 1,2-dibromo 1-chloropropane. Cite down the carbon-1, carbon-2 bond, comma, put C1 in front. Okay, and draw a Newman projection. Okay, so now there are many Newman projections that you could draw here, right? We're just trying to get some practice in drawing a Newman projection. Okay, so this is what I would do. I would first of all give myself a nice little stick figure of 1,2-dibromo 1-chloropropane. Okay, so there's propane, 1,2-dibromo 1,2-dibromo 1-chloropropane. Okay, and I'm going to cite down the carbon-1, carbon-2 bond. I'm putting my eye here and I'm citing down this bond. Okay, so now let's put in some dashing and wedging, right? The Newman projection I'm going to draw here is not the only correct answer. I'm just going through the technique and the method of how you would do something like that. Okay, so now I have to recognize that one of these guys is a dash. Doesn't matter which one. I got in the way there. One of this is a dash and one of this is a wedge. One of this is a dash and the other one is a wedge. It doesn't matter which one, maybe something like that, right? And there's a methyl group there. Okay, and I'm citing down the carbon-1, carbon-2 bond, and I draw this imaginary disc, and the carbon in the front, that's going to be carbon-1. I can see everything bonded to him, so maybe I see the Cl poking down like that. Right, and I have the bromine over here. I'm looking at the molecule this way. I have the bromine on my right and pointing up toward 2 o'clock, and the hydrogen is on the left and pointing up to 10 o'clock. Okay, and see this methyl group maybe would be over here, the Br, and the H down there. Okay, so that's just one of the many, many possible Newman projections that I could draw for this molecule. So my suggestion to you would be to draw a stick figure and then interpret that stick figure, cite down the bond, and then interpret that stick figure appropriately. Okay, so this is how we use the Newman projection is something that is used to show torsional strain. But before we can talk about that, let's look at some vocabulary that's associated with the Newman projection. All right, so the Newman projection, there are a couple of different views here. Okay, this arrangement where it looks like a Y in the front, a Y in the front, a Y in the back, and where these guys are forming these 60 degrees of angles, this is called a staggered conformation. Okay, and the various substituents on this carbon, the vocabulary associated with them is that A on the carbon in the front and B on the carbon in the back, they can form a 60-degree of dihedral angle, right? They look like they're kind of next to each other. This relationship is called gauche. Anyone speak French here? Tell me in the chat, what does gauche mean? Anyone know French? What does gauche mean? Yeah, it means to the left, right? And the proper pronunciation is gauche. Please don't say gouch, especially not when I'm around. Okay, so substituent on carbon in the front makes a 60-degree angle with substituent carbon in the back. That's called a gauche. We say that A and B are gauche to each other in the staggered conformation. All right, another relationship, another vocabulary word associated with the Newman projection is when the carbon in the front has substituent A and the carbon in the back has substituent B, and now instead of forming a 60-degree of angle between them, they form a 180-degree of angle. This relationship, this is said, A and B are said to be anti to each other. So 180 degrees, anti to each other. The other important type of Newman projection is because, remember, getting back to my little model here, what we're saying, what we said is that when these, when bonds are eclipsed, they relieve the eclipsing by twisting out of the plane of the tabletop. So we don't have any eclipses here, we don't have any eclipses here, but we need a Newman projection that shows those eclipses. And so that is this conformation here. This guy, very appropriately, right? This is a staggered conformation as well. This one is called an eclipsed conformation, and there's a little bit of artistry involved here in that we have substituent B is going to be right behind substituent A. Substituent A is on the carbon in the front, substituent B is on the carbon in the back. They're going to be standing right in front of each other, but we want to make a drawing that's beautiful and easy to interpret. So obviously we can't do this. We can't do this. A and B are right in front of each other. Oh, that's A and that's B, right? Can't do that. So what we do is we picture the eclipse, a little bit off eclipse, The implication is that A and B are eclipsed, but we can't draw them that way because that drawing will be ugly and difficult to interpret. So the eclipsed conformation here, we draw A and B slightly off eclipse, but the implication is that they are eclipsed. And notice in my incomparable artistry, what I have shown is that the bonds to A is longer than the bond to B. Why? Because the bond to A is closer to me. And the closer something is to you, the bigger it looks. So I'm drawing this eclipse. I'm trying to come up with a very beautiful and easy to interpret picture in which I'm not showing A and B eclipsed exactly, a little bit off eclipse. Okay, this relationship here, they are said to be eclipsed or sin, S-Y-N, as in the wages of sin are death. Okay, now we're all set up to start talking about torsional strain with the Newman projection, and I'm going to take a 10-minute break now and then put all of this on a quantitative footing. Okay, so I'm going to go have a sip of coffee, 10-minute break. Is there anything I should know about? Can you tell me in the chat? Anything I should know about? Can you tell me in the chat? You can do a Newman projection of sp2 carbon, but it's going to look different. You have you're looking at something maybe that looks like this. Right there, I'm looking at an alkene on edge, right? Not face on edge. My eye is here. I'm sighting down this bond. What I see is H that way, Cl this way. CH3 is in the carbon in the back like that, and H is in the carbon in the back like that. So yeah, there are Newman projections for sp2 carbon. Okay, what else? Anything else I should know about? Speak now or hold your peace for the next 10 minutes. Okay, so my clock says 9:51. I will return at 10 o'clock. Okay, well, now let's put this Newman projection and the idea of torsional strain on a quantitative footing. Let's consider 2,3-dimethylbutane, and we want to cite down the carbon-2, carbon-3 bond, and we want to put C2 in front. And we want to consider a 360-degree rotation of the carbon-2, carbon-3 bond as it spins around. Okay, so what I would do is probably draw a nice little stick figure here. Butane, that means 4 carbons, 2,3-dimethyl, put a methyl group on carbon 2 and another methyl group on carbon 3. And this can be my carbon 2 right here. And I'm going to cite down the carbon 2, carbon 3 bond. And I'm going to follow the rotation of that carbon-carbon bond through 360 degrees of angle. Okay, so the first I'm going to start, it doesn't matter where you start, right? Because remember we said there are many, many Newman projections of the same molecule. It doesn't matter where you start, but I'm going to start at because carbon 2 has a hydrogen on it and only one, and carbon 3 has a hydrogen on it and only one. I'm going to start with and label my conformations based on the relative position of those 2 hydrogens. So first, what I'm going to draw is an eclipsed conformation. So there's carbon 2 in the front, carbon 2, what is bonded to carbon 2? 2 methyl groups. So put a methyl group there, and then another methyl group over there. See, I'm making those bonds nice and long because they're closer to me. And then I have a hydrogen over here. All right, now carbon 3 is in the back of this disk, and I'm just arbitrarily starting with an eclipsed conformation. And I'm going to, and the carbon 3 in the back, he's also bonded to 2 methyl groups. He's also bonded to 2 methyl groups. And there's also a hydrogen there. Okay, so that's an eclipsed conformation. I'm going to call this guy the 0-degree conformation because those hydrogens are making 0 degrees of dihedral angle with each other. And I hope you recognize that this eclipsed conformation is not very happy. It experiences uh, strain interaction, torsional strain and steric strain. These methyl groups are big balls of carbon and hydrogen. They're very close to each other in this conformation. These methyl groups, big balls of hydrogen and carbon, they're very close together in this conformation. So this conformation has some strain. The values of these strain interactions have been measured. And this methyl-methyl eclipse, this guy is worth 11 kilojoules per mole, right? So these numbers in circles that I'm going to write, this is the value of the strain interaction, right? You don't have to memorize any of these numbers. On the quiz on Thursday, I'll give you these numbers so you don't have to memorize any of them, but I'm just telling you this is methyl-methyl eclipse. That's worth 11 kilojoules per mole of strain energy. And it is both torsional strain and eclipsing, torsional strain and steric strain. And then we have another methyl-methyl interaction over here. That's worth 11 kilojoules as well. And here we have a hydrogen-hydrogen eclipse, which isn't free either, because now these hydrogens are close to each other and the electrons around this carbon-hydrogen bond are interpenetrating the electrons around the carbon-hydrogen in the back. So the strain interaction for this guy is worth 4.0 kilojoules per mole. That's the hydrogen-hydrogen eclipse. All right, so now we can total up what is the strain energy of this guy. 11 plus 11 plus 4, that worked out to 26 kilojoules per mole of strain energy. Okay, so that's my first confirmation. Now, my next confirmation, there will be, to follow the rotation around 360 degrees, there will be 6 Newman projections, 3 eclipsed and 3 staggered. Okay, so now what I'm going to do is I'm going to leave the carbon in the back alone, and I'm going to diddle with the carbon in the front. You don't have to do it this way, but this is just going to end up the prettiest picture. So the next confirmation is going to be a staggered confirmation where I'm allowing the carbon-2, carbon-3 bond, this guy here, I'm allowing the carbon-2, carbon-3 bond to rotate in order to relieve the strain interactions. Okay, so I'm going to leave the carbon in the back alone. So the carbon in the back is bonded to two methyls and a hydrogen. And I allowed the carbon in the front to rotate 60 degrees in the clockwise direction. I could also do it counterclockwise. I'm not going to, but I end up, this methyl group is now over here. It went from 12 o'clock to 2 o'clock. The hydrogen on the carbon in the front was at 4 o'clock. It's now at 6 o'clock. The methyl group in the front was at 8 o'clock. It's now at 10 o'clock. I've allowed that bond to rotate 60 degrees in the clockwise direction. So this is a staggered conformation, but it also has strain associated with it because these methyl groups are big enough that they don't have to eclipse each other in order to exhibit steric strain and torsional strain. The methyl group is big enough so that even when methyl groups are gauche, as they are here, we get a strain interaction. So here we have these two methyl groups, they're gauche to each other. That interaction is worth 3.8 kilojoules per mole. These two methyl groups, they're gauche to each other. That's worth 3.8 kilojoules per mole. And these two methyl groups, they're also gauche to each other. That's worth another 3.8 kilojoules per mole of strain energy. Okay, so I'm totaling up all of these interactions. I'm calling this guy the 60-degree conformation because now these hydrogens are forming a 60 degree of dihedral angle, and this is worth 11.4 kilojoules per mole of strain energy. Okay, now I'm going to let the bond rotate 60 more degrees in the clockwise direction. I'm leaving the carbon in the back alone. I'm diddling with the carbon in the front. So this methyl group at 2 o'clock, it's now over here at 4 o'clock. This hydrogen was at 6 o'clock, it's now at 8 o'clock. And this methyl group was at 10 o'clock, it's now at 12 o'clock. This is going to be another eclipsed conformation. All right, so I left the carbon in the back alone. And so I'm drawing this eclipsed conformation, slightly off eclipse, so that I can get a picture that is easy to understand and looks kind of beautiful. And once again, I see more strain interactions. This methyl-methyl eclipse, methyl-methyl eclipse, that's worth 11, right? That's its measured value. We saw that already. And now we have a methyl hydrogen eclipse. And this interaction is worth 6 kilojoules per mole. And here we have another methyl hydrogen eclipse. That's worth 6 as well. All right, total up. This conformation has 23 kilojoules per mole of strain energy. I'm calling this guy the 120-degree conformation. Okay, to follow the rotation around 360 degrees, I need 6 Newman projections, 3 down, 3 to go. The next conformation is going to be another staggered conformation where I'm allowing the bond to rotate 60 more degrees in the clockwise direction. So this is going to be another staggered conformation. I'm leaving the carbon in the back alone all the time like that. And now this hydrogen was at 8 o'clock. It has now moved up here to 10 o'clock. And the methyl groups have followed. So there's another staggered conformation. Okay, and what are the strain interactions I see here? I see this methyl-methyl gauche. That's worth 3.8. I see another methyl-methyl gauche down here. That's worth 3.8 again. I see methyl hydrogen gauche, but the hydrogen is so small that it doesn't provoke this methyl. It doesn't provoke a strain interaction here, only when the hydrogen is eclipsed. So this guy, which I'm calling the 180-degree conformation, he has 3.8 plus 3.8 is 7.6 kilojoules of strain energy. Okay, 2 more conformations, another 60-degree rotation. It's going to be another eclipsed conformation. So this hydrogen was at 10 o'clock. It now is going to be up here at 12 o'clock. And these 2 methyl groups have followed along. I'm leaving the carbon in the back alone. So methyl eclipse there, methyl hydrogen eclipse there, methyl hydrogen eclipse down there, and methyl-methyl eclipse over here. Okay, this methyl hydrogen eclipse, what's he worth? He's worth 6. Methyl hydrogen eclipse, what is he worth? He's worth 6. And a methyl-methyl eclipse, what is he worth? He's worth 11. Okay, so totaling up the strain interactions here, I'm calling this guy the 240-degree conformation, and he's worth 23 kilojoules per mole of strain energy. Okay, last Newman projection. This is going to be another staggered conformation. Okay, the hydrogen, I mean the carbon in the back, I'm leaving him alone. He always looks like this. I'm diddling with the carbon in the front, and now that hydrogen was at 12 o'clock. It's moved over here to 2 o'clock, and the methyl groups have followed accordingly. Okay, so there's my 300-degree conformation. And what are the strain interactions I have here? I have a methyl-methyl gauche. That's worth 3.8. I have another methyl-methyl gauche. That's worth 3.8. And I have a third methyl-methyl gauche here. That's worth 3.8. And so I've seen all of these numbers before. They were up there. This is worth 11.4 kilojoules per mole of strain energy. Okay, and so now the next, another 60 degree of rotation is going to lead me back to the 0-degree conformation. And so the rotation starts all over again. So to portray this 360-degree rotation, I need these 6 Newman projections. Okay, so let me show you some pretty pictures here before we go on. All right, so here's a model. I don't think I did this with Avogadro. I did this with something else. This is eclipsed ethane, where we see these hydrogens are eclipsing each other. And this is like a space filling model. And this isn't really that convincing. It doesn't look like this hydrogen ball has interpenetrated this other hydrogen ball. But remember, what we're looking at here is not the full extent of these orbitals, because this orbital extends out into space to a greater extent than is just portrayed by this white ball. So we have a big cloud of electrons around these hydrogens, a big cloud of electrons around these hydrogens, and they have interpenetrated each other. The hydrogen-hydrogen eclipse is worth 4 kilojoules per mole. But now, when I switch out one of the hydrogens for a bigger methyl group, now the methyl hydrogen eclipse, that was worth 6 kilojoules per mole. That's more strain energy because the methyl group is bigger than a hydrogen. And so here on this model, you can see, oh yeah, definitely. You see how this hydrogen is now, looks like it's kissing this other hydrogen. They have interpenetrated each other's spaces, provoking a strain interaction. And now when I switch out that hydrogen in propane for another methyl group, now I have 2 methyl groups. They're big. They have interpenetrated each other's space to quite a degree. Look at this right here. And so the bigger the group got, we saw from hydrogen to methyl, the bigger the group got, the more important the strain interaction is. The methyl-methyl eclipse is worth 11 kilojoules per mole. It's a lot bigger than the methyl hydrogen or the hydrogen-hydrogen eclipse. Why? Because the methyl group is bigger than the hydrogen atom. Okay, and so here we see the gauche staggered butane, where we have a methyl group on the carbon in the front, and it is gauche to the methyl group and the carbon in the back. The methyl group is big enough so that they don't have to be eclipsed in order to provoke a strain interaction. They can be gauche as well. Okay. All right, so now what we can do is we can take all of this numerology and make a pretty picture. All right, and so this is going to be our energy curve. All right, so along the y-axis, I'm going to put strain energy. And along the x-axis, what I'm going to uh, illustrate is the dihedral angle, right? And this is arbitrary, right? Uh, and so I have data for the 0 degree of dihedral angle. I have data for the 60, for the 120, for the 180, for the 240, for the 300, and for the 360, for the 360, well, that's just equivalent to the 0 degree. Okay, and then I calculated all of that strain energy. So I'm not going to be able to draw this, perfectly to scale, but I'm looking over my numbers here and I see I need something at 26. I need something at 23. I need something at 11.4, and I need something at 7.6, right? And this will be in kilojoule per mole. All right, so that's what I did over here. Now I'm going to plot everything. The 0 degree conformation had 26 kilojoules of strain energy. The 60 degree conformation had 11.4 kilojoules. The 120 had 23 kilojoules. The 180 had 7.6. The 240 had 23. The 300 had 11.4. And the 360, which is the same as the 0, and the 0 had 26. All right, so there's all my data. Now I'm going to hook everything up with a nice smooth curve. And what this curve is showing you is how the energy of the molecule is changing, going up and down as that carbon-carbon single bond rotates. It's a landscape of hills and valleys. The staggered conformations, they're the valleys, they're the relative energy minima. The molecule spends most of its time in the valleys, but not all of its time, because because the molecule has enough energy to surmount the barrier and go from one valley over the hill to the next valley. Okay, so now why is this happening? Because we don't think about molecules in isolation, because when you're in the laboratory and you pour out a bottle of some kind of chemical, you're pouring out 10 to the 23rd molecules, right? You're not dealing with one molecule. Maybe you are if you're in intergalactic space, where the distance between molecules is very, very large in the vacuum of intergalactic space. But down here on planet Earth, that's not what's happening. So here you have a molecule, and it's minding its own business, but it's surrounded by bazillions of other molecules. And one of them comes along and crashes into this molecule, and that's what sets this bond from rotating. And then you have another molecule comes crashing down like this, and that's what rotates this molecule. So we're not talking about one molecule in splendid isolation in intergalactic space. We're talking about molecules here on planet Earth that are surrounded by many, many other molecules. They're crashing into each other, and that is what is setting that is what is making those bonds rotate. The hills, this guy, this guy, this guy, and this guy, these are called transition states. and they're unstable, right? They represent energy maxima. These guys live for about 10 to the minus 14 seconds. And then they rotate, right? They're eclipsed. We're talking about how torsional strain is relieved by twisting. These are the eclipsed conformations. They undergo a rotation and relieve the torsional strain. We can see an analogy to this in daily life. What is happening here? Let's see if I can do it here. See, so here's my little ball here, right? I'm going to throw the ball up, catch it, right? Whoa! So let's look at that in slow motion. So this ball went up, 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 up. It stopped here momentarily. That's the transition state. It's figuring out what to do now. It's going to minimize its energy again by falling back down. So these are the transition states. The molecule spends most of its time in these valleys, but not all of the time, because the molecule isn't isolated. It's being crashed into by a bunch of other molecules, and that's what sets the bond to rotate. Okay. So those are the transition states, and these are the energy minima. So the energy energy of the molecule is changing as that bond rotates, because strain interactions are being provoked and then they are being relieved, and then they're being provoked again, being relieved. And something that we have to consider and something we have to worry about is how fast are these, how fast does the carbon-carbon single bond rotate? So that's what I want to talk about next. How fast do carbon-carbon single bonds rotate? Okay, and in order to answer this question, what we need to use is the Eyring equation. And this is an equation that was developed by Professor Henry Eyring at the University of Utah in the 1960s. And it says, so let me just give you this equation here. You don't have to memorize this, but for the quiz on Thursday, you have to be able to use it. The rate, let me just write the equation, then I'll tell you what all these symbols mean. K is equal to KB T divided by H. E, you remember E from Gen Chem, right? Delta E double dagger divided by RT. So that's the Eyring equation. It's going to tell us how fast these bonds are rotating. Meaning of the symbols. K, that is the rate constant. It's not the rate, it's the rate constant. And this has units of per second, reciprocal seconds. It's a rate constant. It's like your speed is miles per hour, right? Kilometers per second. So that's a rate constant, units of per second. KB, this is the Boltzmann constant. Remember him from Gen Chem? T is the Kelvin temperature. H, that's the Planck's constant. Delta E double dagger, this is called, we can call this, it has various names. We can call him the energy of activation or the energy barrier. Energy of activation. Or we could also call this the energy barrier. And then finally, R, this is the gas constant. So this is the equation that we use to calculate how fast these carbon-carbon bonds are rotating. Now, the only temperature that we care about really is 25 degrees. So if you look up the values of the Boltzmann constant, the Planck's constant, gas constant, all of that, and make sure that you get all the units right and then slam in the temperature, you can calculate the rate constant for these conformational changes at any temperature. But the only thing we really care about is 25 degrees C. Okay, so at 25 degrees C, I did all of that and got all the units right and everything. This is 6.21 times 10 to the 12 e to the minus 0.404 delta E double dagger, and this has units of per second. Right, so this is really the only computational formula we care about. This are the values at 25 degrees C. Okay, so that's the Eyring equation. Now we're ready to implement this Eyring equation and calculate the rate constant for these conformational changes. Okay, so going back to my little diagram over here, I want to calculate how long it takes, how fast going from the 180 conformation to the 300 conformation, right? How long does it take? What is the rate constant for going from one valley to the next valley over this hill? Now, I know how long it takes the transition state to collapse to the 180 or to the 300. That's 10 to the minus 14 seconds. What about going from this valley to that valley? It has to overcome this barrier. So that's what I'm going to calculate. For the 180 conformation to the 300 conformation. All right, so here I had my 180. My 180 conformation was down here, and he was worth 7.6 kilojoules, right? And then I had my 300 conformation. He was over here, and he was worth 11.4 kilojoules. But to go from the 180 to the 300, I had to go over this transition state, which was worth 23 kilojoules per mole. So this delta E double dagger, this activation energy, that's the energy barrier that has to be surmounted in going from the 180 to the 300. So it's this distance right here, this energy distance here. That is the delta E double dagger. That's the energy barrier. That's the amount of energy that the molecule has to have to go from the 180 to the 300, right? It has to experience a collision with at least this much energy to promote it over that hill from one valley to the next valley. And so delta E double dagger is equal to 23 minus 7.6 is equal to 15.4 kilojoule per mole. So notice what this activation barrier is not, right? This activation barrier isn't the energy difference between valleys. It's the energy difference between the hill that the system has to climb over and the energy of the valley that the system started in. 23 minus 7.6. If we wanted to calculate the rate constant of going from 300 to 180, it would be different because the system is starting in a different valley. Okay, so slamming all of this into my Eyring equation, slamming all of these numbers into my Eyring equation, I get that the rate constant is equal to 1.2 times 10 to the 10th per second. And this is at 25 degrees C. Well, I've just said, and we've just come up with something earth-shaking, is that the bond is spinning 12 billion times per second at room temperature. So going from the 180 to the 300, that happens 12 billion times per second. The rotation of the carbon-carbon single bond is unimaginably fast. And something that people always ask me will be, well, okay, we just calculated the rate constant of going from here to here. What would be the rate constant of going from here all the way? Well, it would just be maybe 3 times this, right? The Eyring equation is not defined for a multi-step process like that, only for this single step, but the number is still huge, right? 12 billion times per second at room temperature. So if we can play around with the Eyring equation and come up with maybe some other values. So maybe what about at 77 Kelvin, right? And why did I choose 77 Kelvin? What familiar material has a temperature of 77 Kelvin? Anyone know? You've all heard about it. What has a temperature of 77 Kelvin? Tell me in the chat. Maybe you know. Oh, dry ice. No, not quite. Close. Oh, yeah, liquid nitrogen. Exactly. So if I were to take my molecule and immerse it in a liquid nitrogen bath, what would the Eyring equation say about how fast those bonds are rotating then? Well, this is slowed way down to 57 times per second. So this is at 77 Kelvin, which is the same as minus 196 degrees C. So as the temperature goes down, the rate of the rotation slows down. Why? Because now at this lower temperature, this molecule is being collided into by a lot fewer fast-moving molecules. At that low temperature, the molecules don't have a whole lot of kinetic energy. So when they slam into each other, it can't get that bond rotate. How about let's go into the vacuum of intergalactic space? What's the temperature of intergalactic space? Tell me in the chat. It's also called the cosmic background radiation, if you know about astronomy. What's the temperature of intergalactic space? 0 Kelvin? No, not quite. A little bit warmer than that. How about 4 degrees Kelvin, right? Arno Penzias of Bell Labs, who figured this out in the 1960s, this was worth a Nobel Prize. At 4 degrees Kelvin, this is intergalactic space where the distance between molecules is many, many kilometers, where there are very few collisions. What is the rate constant then? 5 times 10 to the minus 191 per second, right? In other words, in intergalactic space, the molecule is frozen, it's rigid, it's not rotating. right? But down here on planet Earth with the rest of us, the molecule is spinning very, very fast. Okay. So now let's finish up talking about the carbon-carbon double bond and rotation about the carbon-carbon double bond. Summarized in one sentence, alkenes don't rotate. The carbon-carbon single bond is rotating at an unfathomable fast rate at room temperature, but not the alkene. So if we could imagine something like this, and then rotate around that carbon-carbon double bond, where now the methyl groups are on opposite sides. Well, the activation barrier for this process, the delta E double dagger, is 264 kilojoules per mole. What was the activation barrier for the single bond? Oh, an order of magnitude less, right? Only 15.4 for our example here, but here it's 300, here it's about 260 kilojoules per mole. Plugging that into the Eyring equation, how fast does a carbon-carbon double bond rotate? 3 times 10 to the minus 34 times per second. And this would be at 25 degrees C. So this is a tiny, tiny, tiny number. In other words, the carbon-carbon double bond does not rotate at room temperature, or really any other, which is the temperature that we're most interested in. The alkene is configurationally and conformationally stable, right? So single bonds rotate and single bonds rotate very fast, double bonds don't. Okay, now we want to get into another issue with the ring strain. All right, so let me show you some pictures here. Don't have time to talk about any of that. Okay, cyclopropane. It's destabilized by many hydrogen-hydrogen eclipses. It's also destabilized by ring strain, right? The angle in the interior angle of that equilateral triangle is 60 degrees, but here we see sp3 hybridized carbon wants to be 109.5. And so what I did in my little model here is I tilted it on the side where you can see the hydrogen-hydrogen eclipses. So that's destabilized. Destabilized or not, cyclopropanes occur very frequently in nature. This is, we see the cyclopropane moiety over here. This is a pyrethrin. This is an insecticide. Marigolds, these are pictures of a picture of a marigold. They have this insecticide in them. So even though the three-membered ring is very strained, nature has no trouble making them. And also they're pretty easy to make in a lab. So this is an example of jazoic acid. Look at all of those cyclopropanes. I guess it's called this because it's supposed to imitate the teeth of a shark. Okay, the four-membered ring, cyclobutane, the planar cyclobutane has a lot of carbon-carbon and carbon-hydrogen eclipses, but now cyclobutane is flexible enough that it can pucker to relieve the eclipsing interactions. So if you can make a physical model of cyclobutane, it doesn't want to be planar. It doesn't adopt this planar conformation. It's flexible enough that it can pucker. So that relieves some of the uh, some of the hydrogen-hydrogen eclipses. So here's a molecule that has the cyclobutane moiety in it, alpha-berberine. It's the molecule, one of the molecules that's responsible for the flavor of bourbon whiskey. So again, nature has no trouble making these cyclobutane rings, and they're fairly easy to make in the lab. Okay, next, cycloalkane is cyclopentane, which is once again flexible enough that it is not going to be planar. It can adopt a puckered conformation that relieves a lot of the hydrogen-hydrogen eclipses, but it doesn't relieve all of them. So cyclopentane has some strain energy associated with it. And cyclopentanes, these are everywhere in biochemistry and in organic chemistry. Maybe you've heard of these prostaglandins. These are physiologically active 5-membered ring systems. PGE2, this causes fever and pain. Aspirin, naproxen, ibuprofen. These are PGE2 synthetase inhibitors. This molecule here, this PGE2, this is what causes a headache. This is what causes certain kinds of pain. The enzyme that constructs this molecule is disabled by the non-steroidal anti-inflammatories, right? Caverject is PGE1. This is an early erectile dysfunction medication. When this Caverject is injected into the, I'm going to use some adult language here. I hope you can handle it. When this Caverject is injected into the base of a flaccid penis, it produces an erection lasting for 8 hours. So this is another example of a molecule that has that 5-membered ring. But now, finally, and at last, we have gotten to the granddaddy of the rings, and this is cyclohexane. So now we're going to talk about cyclohexane. Planar cyclohexane has lots of eclipsing and angle strain, right? If we were to draw cyclohexane and get all of the carbon-carbon bonds to sit on a tabletop, we would get something that looks like that. And now decorate with all of the hydrogens, and we have hydrogens there, hydrogens there, hydrogens there, hydrogens everywhere, all of these hydrogens. What we see is that's an eclipse, that's an eclipse, that's an eclipse, that's an eclipse. You have just tons and tons of eclipses here, and all of those provoke a bad strain interaction. Not only that, but planar cyclohexane, what's the interior angle of a hexagon? 120 degrees. That's a deviation from ideality. So planar cyclohexane does not exist. It has way too much strain energy. What cyclohexane does in order to relieve all of this interaction is it puckers. It puckers into what is called the chair conformation. And the chair conformation looks like this. All right, and we have lots and lots to say about drawing these. And so so cyclohexane is not plain, right? It has this chair conformation. And chair cyclohexane, the strain energy of chair cyclohexane is 0. Puckering into this conformation relieves all of its strain. Okay. So there's chair cyclohexane. It's called chair cyclohexane, I guess, because, I guess like this is where you would sit down here. There's the backrest. There's like a place, prop up to see your feet. Chair cyclohexane. This is a picture. This is a shape that we've seen countless of times already. But it's not until this moment that we recognize what it is we were looking at. Chair cyclohexane. Where have we seen this before? Yeah, the Budweiser logo. Yeah, I don't know why they have a chair cyclohexane in there, but yeah, there it is. We can't get the science of cyclohexane down unless we get the art of cyclohexane down, right? So it's important to be able to draw chair cyclohexane in a appropriate and presentable way. So let's talk about the art of cyclohexane. Can't get the science right unless we have the art right. Okay, so actually the chair cyclohexane, there are actually 2 chair cyclohexanes. There's the so-called left-handed chair and the right-handed chair. Now I'm right-handed, so I draw the right-handed chair a lot better than the left-handed chair. Okay, so how do we draw this chair cyclohexane? This is something I need for you to practice, right? To be able to draw these. Make a V, not up and down V, like you would see on the printed page, but a V that is kind of tilted like that. And now 2 parallel lines, not too long, and then cap it off with an upside down V. So that's the right-handed chair. Now, I habitually always put a big fat bond down here, a big fat bond on one of these parallel lines down here, and another big fat bond over here. And what these fat bonds are telling you is this is the part of the molecule that is closer to you. And those bonds are big and fat because as something gets closer to you, it gets bigger. So these fat bonds here, that's the front of the molecule. And these skinny bonds in the back, they're farther away from you. That's the right-handed chair. Now there's also a left-handed chair, which is harder for me to draw because I'm not left-handed. And I start out with a little V like that, not an up and down V the way you would see on a printed page, but tilted, 2 parallel lines, not too long, and then close it off with another V. And now these 3 bonds down here, I habitually always draw these big fat bonds down here because that's the part of the molecule that is closer to you. Okay, so you need to practice drawing these chair forms. But there's much more to the art of cyclohexane because on each of these carbons have hydrogens bonded to them, and we need to be able to draw those correctly. And so the hydrogens that we would draw on the chair cyclohexane are divided into 2 groups, the so-called axial bonds and the equatorial bonds. Okay, so now let's look at the axial positions. So I'm going to draw the chair cyclohexane, right-handed chair, fat bonds here. And now this carbon up here, let's agree to call this an upward pointing carbon. To get to this carbon from any other carbon, from the neighboring carbons, you have to go up. So you're here, you want to get there, go up. You're here, you want to get there, you have to go up. That's an upward pointing carbon. This is a downward pointing carbon. To get to this carbon from the neighboring carbons, you have to move down, 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 down. The axial bonds on an upward pointing carbon point straight up. The axial bond on a downward pointing carbon points straight down. Upward pointing, straight up. Downward pointing, straight down. Upward pointing, straight up. Downward pointing, straight down. So if this cyclohexane had hydrogens on it, this is where some of them would be in the axial positions. The other kinds of bonds here are the equatorial. Try again. Equatorial positions. And these are harder to draw. There's my chair cyclohexane, right-handed version, fat bonds. And now in your imagination, divide the chair cyclohexane into the left-handed portion and the right-handed portion. So I'm just going to draw a light dotted line like this. The axial position, the equatorial position, the equatorial bond on a carbon on the right of this imaginary line points to the right. Points to the right. Points to the right. The equatorial positions on the carbons on at the left of this imaginary line point to the left, point to the left, point to the left, point to the left. So that's what the equatorial bonds look like. Let's put it all together. Remember the hybridization state of the carbons in cyclohexane are sp3 hybridized. They have to look like a chicken foot, right? Axial, equatorial, axial, equatorial, axial, equatorial, axial, equatorial, axial, equatorial, axial, equatorial. So you see how all of these carbon atoms have that distinctive chicken foot shape of sp3 hybridized carbon? So I need for you to practice drawing these chairs and drawing the axial position and the equatorial position. Because I'll tell you on that quiz on Thursday, something like this is not going to be acceptable. Something that looks like this is not going to be acceptable, right? So get it to look like this. We have a lot more to say about the art of cyclohexane, and I think we'll continue and conclude talking about cyclohexane tomorrow. Okay, so we're going to stop there because